This video gives an overview of mass spectrometry. Mass spectrometry, or mass spec for short, also just abbreviated MS, is used to determine the molar mass and formula for a compound. The process involves vaporizing and then ionizing a compound, which then undergoes fragmentation. And then in the instrument, the masses of the ions are detected and graphed. This diagram shows a representative illustration of a mass spec instrument. In this, a sample is inserted at the inlet, and the sample is vaporized, and then it's bombarded by electrons and ionized. So the electrons are produced by a heated filament, such as a tungsten filament. These electrons that are bombarding the molecules are energetic enough that they will kick off an electron from the organic molecule, and as a result, a positive ion is formed. This ion is called the molecular ion, or sometimes it's called the parent ion. These ions are very unstable, and some of them will break up into smaller pieces known as fragments. The ions leave this ionizing chamber and are accelerated through the instruments using a series of slits. Then they enter a magnetic field, which is produced by the magnet shown here. And based on their mass to charge ratio, when these enter the magnetic field, they will be deflected to different angles, with lighter masses being deflected to a greater degree than heavier masses. By varying the magnetic field, we can sort these ions and direct one mass to charge ion through this slit into the detector where it's detected. There are a large variety of methods for ionizing molecules, but the most common is electron impact, which is what I was describing in the last slide. So in this, you bombard a sample with an electron beam, and as a result, an electron is ejected from the molecule. So for example, if you have this representative organic molecule, you would bombard it with a beam of electrons, and then an electron would be ejected to form a radical cation. So you've lost one electron, which is why it's now a radical, and if you lose an electron, you're going to form a positive species, which is why it's a cation. Now, these can be tricky to draw because they defy our common understanding up to this point of what Lewis structures look like. So you can draw it like I've shown here, but sometimes it's also drawn like the typical structure with the brackets and a dot plus on the outside indicating it's a radical cation, so it doesn't really look like that. The mass of the radical cation that's initially formed is the same as the parent compound because the mass of an electron is very, very tiny, so it's essentially negligible. Therefore, if we can determine the mass of the radical cation, we can determine the mass of our compound. If this radical cation remains intact by the time it gets to the detector, it's known as the molecular ion or the parent ion. This is really useful because if we know the molecular ion mass, we know the mass of our compound. Now, as you might imagine, a radical cation is pretty unstable, so it will typically fragment and break apart into smaller pieces. So in this example, this radical cation breaks apart into a radical and a carbocation. The ions that are deflected by the magnetic field are deflected according to their mass to charge ratio. Therefore, if there is no charge, they will not be detected. So lighter fragments are deflected to a greater degree than heavier fragments. In the spectrum that we get, the output from this experiment, we have a graph where on the x-axis is the mass to charge ratio, and the y-axis we have the relative abundance. So this is going to give us a series of peaks for each ion that is detected. There are a couple terms that we use. One is the base peak. The base peak is defined as the tallest peak in the spectrum. Therefore, it's the most abundant fragment. Now here we see that the base peak is at a value of 16, which is the mass of methane. So in this case, the base peak is also the molecular ion peak. These other peaks shown here would be fragments. And I'll talk about what this peak is to the right of the molecular ion peak in a minute. So those other peaks in that spectrum that we just looked at represent fragments. So this molecular ion can lose hydrogens to give a mass to charge ratio of 12, 13, and 14. Okay, so my question to you is, why do we use specific isotope masses when calculating the masses of peaks that we see in the mass spectrum rather than the average weight shown on the periodic table? And here you see a table of various isotopes. There's carbon there, there's carbon 12, carbon 13, carbon 14. But when you are looking at masses in a mass spectrum, we're only going to use specific isotope masses to get to the mass of the peak. And why would that be? I want you to think about how the instrument works, and you can put your ideas, your thoughts in the chat. Mass spec is a relatively sensitive analytical method, and it's used in a variety of contexts. It's used in drug discovery, it's used in biotech to do analysis of macromolecules, it's used in the clinical setting, it's used in the environmental setting to do drug testing, to evaluate water quality. It can be used in forensics for explosive detection and in geological fields, for example, to evaluate oil composition. In airport security, specialized mass specs are used to detect explosives on the surface of luggage. Let's look at this example mass spec for benzene. So over here at the right, at this would be 75, 76, 77, 78, we have the tallest peak, which is by definition our base peak, is our most abundant peak. This also corresponds to the mass of benzene. 6 carbons times 12 AMUs per carbon plus 6 hydrogens equals 78. All of these other peaks correspond to fragments of benzene. Now with benzene, the base peak was the molecular ion peak, but that's often not the case. So if we look at pentane, the mass spectrum shows that the base peak is at 43. That is not the mass for pentane. So indeed, the molecular ion peak is way over here, and it's quite small. So this shows you that the parent ion for pentane fragments quite easily. The first step in analyzing a mass spec is to identify the molecular ion peak, because that's going to tell you the molar mass of the compound. This is one of the key pieces of information you can get from mass spec. Also, you should know that an odd-massed molecular ion peak generally means that there's an odd number of nitrogen atoms. An even-massed molecular ion peak generally indicates an absence or an even number of nitrogen atoms. So, for example, pentane has a molecular weight of 72, which is an even number. However, if we replace one of the carbons with a single nitrogen, we get an odd number for the molecular weight. However, if we add 2 nitrogens, we're back to an even number. Now, I mentioned that there's this little teeny peak to the right of the molecular ion peak. So what is that from? This is called the M+1 peak. The M+1 peak results from the presence of the isotope carbon-13 in your sample. So remember that carbon has 3 isotopes, carbon-12, carbon-13, and carbon-14. The weight you see on the periodic table is an average of those isotopes taking into account their natural abundance. However, when we're thinking about a mass spec, that mass spec is going to detect the exact mass of the particular carbons in your sample. So a particular carbon is going to be either carbon 12 or carbon 13. There's so few carbon 14 atoms, we don't have to worry about it. So about 1% of all carbon atoms are carbon 13. So as a result, whenever you have a carbon containing molecule, you're going to have a peak to the right of the molecular ion that is 1 atomic mass unit higher than the parent ion peak. And that's because 1% of methane molecules that pass through the instrument will have a carbon 13 atom, not a carbon 12 atom. Now, if you increase the number of carbons in your molecule, there's more chances that those carbons could be carbon 13 atoms versus carbon 12 atoms. And this is just a result of statistics. So as the number of carbons increase, the height, the relative abundance of that n+1 peak will also increase. And we can use that to our advantage because we can compare the height of the molecular ion peak and the n+1 peak to determine how many carbons are in the molecule, which will help us figure out the formula. And we're going to do some exercises in class on this. Okay, here are a few more discussion questions for you. We talked about the n+1 peak, and that is a result of carbon 13. Do you think that a peak might arise from carbon 14? If so, do we observe it frequently? Now, to answer this, it would be helpful to look at the isotope abundances. Then my second question is the n+1 peak always due to carbon 13? Could it be due to something else? And in answering that question, I want you to look at this table of isotopes. Also, what other elements might give rise to n+1, n+2, n+3, n+4, etc. peaks? So put any thoughts or questions or answers you have to these questions in the chat. Thank you.